Hello everyone. In this video, you will learn how to design the cantilever beam, and we'll also cover the following key points: step by step determination of load calculation and the maximum factor design moment of the cantilever beam. And the second one is to design the beam tension steel reinforcement. So let's dive into our problem. Design the cantilever beam shown in the figure below to determine the required longitudinal tension reinforcement. The beam has a cross-section of 300 mm by 600 mm, and it carries a triangular distributed load of 15 kN per meter dead load and 12 kN per meter live load, in addition to a 22 kN concentrated load applied as shown. Use normal weight concrete with FC prime is equal to 228 megapascal. Reinforcing steel with Fy is equal to 420 megapascal, and a unit weight of concrete is 24 kilonewton per cubic meter. So here we have a load diagram, and we have a cantilever, a 4-meter span, and we have a triangular distributed load, and also the concentrated load applied at the pre-end and the intermediate, which is 26.4. So all the loads reflected in here in our diagram is a factored load. So here we are given the dead load, which is 15 kilonewton per meter, and the live load of 12 kilonewton per meter. So we have 22 kilonewtons. These are all the service loading. So we have 28 megapascal, Fc prime and Fy is equal to 420 megapascal. And we have a 24 kilonewton per cubic meter for the unit weight of concrete. The beam size is given as 300 mm by 600 mm. So let's get started with our solution, load determination. So first of all, we need to check the required depth of the beam based on the ACI 318, table 9.3. Point 1. So for cantilever beam, the required depth is equal to L over 8, and that is 4 meters over 8. We have a 4-meter span, and that is equal to 0.5 meter, which is less than to our depth of beam that we used, which is 0.6 meter. So we are okay for this requirements for the depth of beam. So now we will calculate the factored triangular distributed load based on 1.2 dead load and 1.6 live load. So 1.2 times 15, the dead load, plus 1.6 times 12, the live load, and that is equal to 37.2 kilonewton per meter. So that is our factored triangular distributed load, which is this one here. So for PU, which is the dead load, is equal to 1.2 times 22 kilonewton. That is equal to 26.4. So we have applied here 26.4, both of that concentrated load. Now the beam self weight, we have to account also as dead load 1.2 times 0.3 times 0.6, and that is multiplied by 24, and that is equal to 5.2 kilonewton per meter. And this is a uniformly distributed load. So the maximum factor design moment at the support, taking moment at the face of the cantilever beam, mu, is equal to 0.5 times 4 times 37.2, which is the triangular load here, times the moment arm, which is 1/3 of the span, or 4 meter over 3. plus 26.6 kilonewton times 2 meters, which is this one, moment arm is 2 meters, plus 26 times 26 kilonewton times 4 meters from here to there. So the total maximum moment is equal to 256 kilonewton meter. So now we will determine the tension steel reinforcement. So to determine the steel ratio using the formula, first we need to assume that tension controls, so that Fs is equal to Fy and P is equal to 0.9. So we will estimate first the effective depth of the beam, which is equal to 600 minus 40 mm, the clear cover, minus 25 mm over 2, assuming that we'll use 25 mm rebars, and that is equal to 548 mm, the effective depth. So the steel ratio, based on the flexure formula, if we express this equation into the steel ratio, we will come up the quadratic equation. So to solve the steel ratio, we need to determine first the value of M as well as the value of Rn. So let's proceed with our calculation. M is equal to Fy over 0.85 Fc prime, which is equal to 420 megapascal over 0.85 times 28 megapascal, and that is equal to 17.65. That is the value of our M. So for Rn, that is mu over P BD squared. So that is 256 kilonewton meter times 10 to the power of 6 all over 0.9 times 300 times 548 square is equal to, that is equal to 3.16. That is the value of Rn. So now we can proceed to determine the value of our steel ratio, which is equal to 1 over 17.65 times 1 minus the square root of 1 minus 2m, which is 17.65 times 3.16, the Rn, over 420. So the steel ratio is equal to 0.00816. Now, we will check this based on our minimum requirements as per the ACI 318 section 9.612. So we have here 1.4 over Fy, and that is equal to 1.4 over 420 megapascal, and that is equal to 0.0033, which is less than to our actual steel ratio based on our calculation. So we are okay to use this one, which is governing one. So the second one, we have the second provision of 0.25 times the square root of Fc prime over Fy, which is equal to 0.25 square root of 28 over 420 is equal to 0.00315. And still, this is less than to our actual steel ratio. Now, the actual required steel reinforcement is equal to rho BD, which is equal to 0.0081 times 300 times 548. So the actual required steel reinforcement is equal to 1,332 mm squared. Now, if we use the 22 mm diameter bars, it requires 4 pieces, or the total area of 1,920 mm squared, which is greater than the required of 1,337 mm squared. So we are okay to use this reinforcement. So here we have the section of the beam. The placement of the reinforcement is on the top because the tension in cantilever beam is on the top of the beam, because that is the required reinforcement here. Now we can we will check the strain, tensile strain of the reinforcement to make sure that the steel has yield. So to calculate the tensile strain, first we need to determine the value of A, which is the stress block, and that is equal to ES times Fy all over 0.85 Fc prime times B. So A is equal to 1920. No, this is not 100,000. 9,000. Okay, that's correct. 9,000, 1920. That is the actual steel reinforcement times 420 over 0.85 times 28 times 300, the width of the beam, and that is equal to 113 mm. So that is our the value of stress block A. So now we can determine the value of C, which is the location of our neutral axis. So the value of C is just equal to A over beta. Beta value of beta here is 0.85. That is for strength of concrete equal to or less than 28 megapascal. And that is equal to 113 over 0.85. So the C value is equal to 133 mm. Now we can determine the value of our tensile strain because we have already determined the value of A and C. So we can determine the tensile strain by ratio and proportion. So simplifying that equation for ratio and proportion, that is equal to 0.003 times D minus C over C. So that is equal to 0.003 times 548 minus 113 over 113, that is equal to 0.0115, which is greater than 0.005. So which means tension control. So our assumption of Fy and P is correct. So that's the end of our video, guys. Please, if you enjoy this video, or if you find this helpful, please don't forget to like or subscribe. Thank you for watching. See you next time. Bye bye and God bless.